1.5, velocity and other rates of change. Honestly, as we get further and further into this, like into calculus, it is kind of neat what you can do with this stuff, okay? What this stuff can do for you. Like, for example, we're going to be finding today instantaneous velocity. We're going to be able to figure out exactly the velocity of something at a given time point, okay? Which to me I think is interesting because when you think about driving a car, it's constantly changing. And that's what this is talking about. Is if a car is driven on a highway for 3 hours, the distance covered 270 kilometers, easy to find the average velocity of 270 divided by 3, the average is 90. But guys, we know that it's common sense that your car is not going to be 90 flat for 3 hours straight, okay? Unless you have really good cruise control and really straight, no hills and nothing else is happening, okay? But in general, you're going to have some stoppage and some starts and some speeding up and passing, all those things. So this is the average, not the instantaneous. Okay, so that's what this is explaining here. So, for example, suppose that a ball is dropped from the upper observation deck of a CN tower 450 meters above the ground. How fast is the ball falling after 3 seconds? So in trying to solve this problem, we used the fact discovered by Galileo almost 3 centuries ago that the distance fallen by any freely falling body is proportional to the square of its time it has been falling. So this neglects the air resistance, so we're pretending there's no resistance or wind. Okay, if the distance fallen after t seconds is denoted by s equals f of t, then we can represent it in this equation here of 4.9 t squared. Okay, so what that means for us is we're still going to look at, so this is the function we're going to look at. If we were going to do it for 3 seconds, okay, we would go ahead and try to figure out some type of change. So before, like kind of this is the part that, like, again, I come back to his book where we asked the question, but we talked about why are we going on the parabola versus why we aren't. Okay, well, right now we're not going for instantaneous, we're looking for average. Okay, so how far, we're going to look for the average to start. So we can take the points in terms of any time points that we want. So what I'm saying is I could do 4 seconds minus 3 seconds to figure out that rate of change. Now, rate of change is not going to be super accurate. And as more and more that we look at different points, okay, like in that very beginning, that picture where it showed all the different lines that kept tilting closer to what the answer was, we're going to get to that closest point possible, which will be the limit. Okay, so for example, to doing this one, simply we're going to do the easy one first. Okay, we're going to do f of 3.1. I picked 3.1 because it's close to 3. Minus f of 3. Because that's the time we're looking at, all over 3.1 minus 3. So this is a roughly close gauge to what's happening at that time point. So when you plug these in and you work this out, just mathematically wise, I'll just kind of let you know what it works out to. It works out to 29.89 meters a second. Okay, is that speed at that given time point. But that's our rough estimate, right? Because we're using 3.1 to 3. We also could do 3.01 to 3 and then 3.001 to 3 to really find out what's happening there, right? At the limit as we get closer to that point. So, sorry, I already did that work. We just did this. I want to get to this chart. So here is the time interval between 3 and 4. If you did the average velocity between 3 and 4, it'd be 34.3. As we tighten it down to the 3 and 3.1, we got 29.89. Between 3 and 3.05, and it keeps going. As you can see, it's getting closer and closer to 29.4. So 29.4 is what it's going to be approaching. Now 29.4 is going to represent that instantaneous velocity at 3 seconds. These are average on the time interval. This is approaching the actual instantaneous velocity at that time. Okay? So you need to understand it's a relationship of you're using the limit to find it exactly, like this is what our limit's going to approach once we do it. Okay? But the point is that these are time intervals can still yield you results that are helpful. Like average velocity as approaching to 29.4 for instant velocity. Okay? And so we can also do it in terms of the limit, which we'll do next here. Okay, so Hold on one second. Okay. All right, so we're going to start it up here in terms of, again, change in speed over change in time. And so we're going to use this here, which is what you're used to, right? The one we just used from like the last lesson, 1.5, or 1.4, excuse me, this is 1.5. So it'd be f of 3 plus h minus f of 3 all over h. And that's the limit as h approaches 0. So if I plug this in, remember we're using still the same, we're using that 4.9 t squared. That's our function. So that means it's going to be this. Okay, that's where we're at. For this example, yes. Not always for all velocities, no. You'll be given them most likely, yeah. That's just the setup they gave from Galileo for a falling object. It's 4.9, so 4.9 will generally be what we use for falling objects, but I'm saying we're going to be doing velocities of things that aren't always falling. So, but you don't have to memorize that kind of stuff. You'll be given what you're taking the limit of in terms of the function. So h is the change. Right. The change in height, like that's the from the picture from before. The change. Well, actually, it's the complete change, the up and over change, like the slope.
Okay, so the start from where it started falling to where is what you'll find.
Yes, but it's generic on purpose because we're trying to figure out the limit, which will give us closer to this rather than estimating.
Oh, okay.
Right? That gives us, because we're going to try to get rid of the h's, we're going to take the limit so that it cancels so we can figure out what it's actually doing at that point. So we're hoping to get 29.4 here because that's what it looks like it's approaching by our estimation here in our table. Does that make sense? So it's the same thing we were doing last time, Dana, with the how we use plus h, or the one I did in the warm-up, which I didn't use the plus h one. Okay, so what we're going to do now is going to multiply this out, multiply that out. So I'm going to go to the next page here. So when we do that, we should get so looks like what I did first was I pulled a 4.9 out because there's 4.9 on both of them. And then I get 9 plus 6h plus h squared minus 9. So that 3 squared back here, this guy right here, I took these 4.9 out right off the bat so I can get these to simplify. So I just pulled a 4.9 out. Now, if you didn't do that, it'll still work out. You're just going to have uglier decimals, so it's not a problem if you forget to do that. So the reason this is helpful because you can see my 9s go away, and so then I have just this. Okay. So are we stuck, or what do we do now? Pull out an h, right? So we still pull the h out, just like we did before. So 4.9h times 6 plus h all over h. Those are gone. And now we can take that limit. Limit as h goes to 0. Remember, this was here the whole time. I just don't keep writing it. Okay, 4.9 times 6 plus h. So essentially it's going to be 6 times 4.9, so it's just going to be exactly 29.4. Okay, so you can see what it was approaching on our table is what we got. So we feel pretty good about that. Okay, any questions there? Yep.
So lim of h goes to 0 equals change in speed over change.
Great. And remember, there's 2 implicit formulas you can use. You can do f of x minus f of a, and a is the time value or the x value over x minus a, or f of x plus h minus f of x over h. That limits h approaches 0. So in the warm-up, we did the other one, f of x minus f of a. This one's doing the h plus 1. in this case 3 plus h, because 3 was the starting point. Okay? Good questions, good questions. All right, if the time interval is very short, then h is small, so 4.9h is close to 0. The average velocity is close to 29.4 meters per second. The instantaneous velocity, when t equals 3, is defined by the limiting value of these average velocities. So what we did was, at the instantaneous velocity is essentially what we found. It's instantaneous because it's that single point. We talked about tangent line, that's exactly what we're talking about. We just did what we did from last lesson because that's the tangent spot, that's a single point, that's the instantaneous velocity. So when you see this next formula here, right here, I'll come back to this picture. Instantaneous velocity is pretty much the same thing we just did in 1.4, the tangent line. Limit as change in t goes to 0. Change in s over change in t is limit as h goes to 0 of a plus h, a over h, which we did that previous lesson. Okay, so let me go back to these pictures here. So 4.9t squared is this parabola here. Here is 3. This represents the 3 plus h. Now, you're saying, what does h represent? That's the thing we're saying is generalized so that we don't have to be boxed into one answer. When you're boxed into one number, that gives you something that's close to it, but not quite it. That's why our table was those numbers that were really close to it. We did 3.01, 3.1, 4, etc. And those slopes going through those were pretty close, but not quite 29.4. Okay, so when we actually generalize it and put the h there, it allows that rate of change to be figured out through limits. Okay, let me pause there. See some confused faces. I'm trying to make the connection here, but any questions? So what 29.4 represents is the instantaneous velocity at that point. It is exactly a tangent point, correct. Because we're figuring out, that's the cool thing about calculus, we're figuring out what that velocity is the exact time based on the information given. Okay? Because this is a free-falling object, right? So a free-falling object is going to have a somewhat constant speed, so we can figure out that. We're not talking about a car example. That changes all the time. We can't figure that one out, okay? But this is a free-falling object, and we can find the instantaneous velocity at a time point for that falling object. Okay? Okay. All right. Sorry. In general, suppose an object moves along a straight line according to the equation s equals f of t. So then the average velocity over this time interval would be that, which we're familiar with. We just used it. Okay? What you guys want to have down, you can write this down if you want, just instantaneous velocity example. And this is just kind of showing it from a different type of curve. You do need to use this one for this one. Okay, I'll pause the video if you want to copy this down. I know it's in your book, but instantaneous velocity. All right, as we continue here, so example 2. The displacement in meters of a particle moving in a straight line is given by s equals t squared plus 2t, where t is measured in seconds. Find the velocity of the particle after 3 seconds. Okay, so we are finding the velocity of the particle after 3 seconds. So it wants to know, is that instantaneous or an average? Just by the way it's like asked, what would you think? Yeah, it's instantaneous. It wants to know after 3 seconds. So what's happening right at 3 seconds? Okay, so we are going to go f, just the one we just did, a plus h minus f of a all over h. So again, we're putting this, we're using, so a in this case is 3. Okay, so we can erase this, we can put 3's in. This goes in for t. So we're going to have 3 plus h squared plus 2 times 3 plus h minus f of 3. So what do I get when I put 3 in? 3 squared is 9 plus 6, I get 15. All over h. Okay, have I lost anybody yet? Okay, so all I've done so far is I've plugged 3 plus h in for t. That's what it would look like. I plugged 3 in for t. You get 15. So now I got to simplify. Okay, so I got to do this guy. So it's going to be 9 plus 6h plus h squared plus 6 plus 2h minus 15. That's my top. You can immediately see, or not immediately, but you kind of get happy because I see 9, 6, and a minus 15. So my constants will go away again. So that's gone, that's gone, and that's gone. My like terms, a 6h and a 2h, I have an 8h. This is where we're at. Yep. Yeah, and we'll figure out how to do stuff with that later. Okay. Yep.
So S is basically fx. Is that how you subdivide it?
S, this right here?
No, the one up top, like the one, that one.
Yeah, that's essentially y.
Okay.
And these are x's, yeah. Times a function of speed here. Okay, so pull your h out. So you get your h out, you get h plus 8. And now we could do our limit. Eight meters per second is the instantaneous velocity at that time point. We good with that one? All right, we got. Okay, let's just summarize this. It's in your book. But I'm just going to summarize this, just kind of talking about comparing them. So suppose that y is a function of x. We write y equals f of x. If x changes from x1 to x2, then the x changes x2 minus x1, which we understand that. Same thing for changing y. It's f of x2 minus f of x1, which in other words is just, this is just y2, y1. It's the same thing. Okay. These are called the average rate of change. So we're going to talk about finding average rate of change. So now that difference there is, it's actually easier. What I was just telling Emily is that when you're given 2 time points that you want to find the average rate of change between, you plug both those in. You don't have anything that's an unknown. Okay? It's simply going to be kind of like our warm-up, except for instead of f of x, I'd put like, if I want to find between 6 seconds and 3 seconds, I'd go f of 6 minus f of 3 over 6 minus 3. If you're saying, well, hey, that's just a slope formula, you're exactly right. Slope formula is the average rate of change. Because what do we find slopes of? What do we find the slope of? What is it? The word I'm looking for is a line. Okay? We're looking for a line. Why can we find the average slope of a line? Because the line slopes what? The same all the time. So if I take any 2 pieces of it, I get that average. Okay? So same thing here. We're using essentially the slope formula almost in an applied sense. Okay? Any questions on that? I know that's kind of maybe a little more obvious, but so here is the example. This is in your book, okay, Dana? Sorry, I know I'm going a little fast. Okay, so the top there is just your rate of change. This is what I'm talking about. A thermometer is taken from a room where the temperature is 20 degrees Celsius to the outdoors where the temperature is 5 degrees Celsius. Temperature readings T are taken every half a minute and are shown in the following table. The time T is measured in minutes. Find the average rate of change of the temperature with respect to time over the following intervals between 2 and 4. So you'd simply do for 2 and 4, okay, would be T of 4 minus T of 2 over 4 minus 2. So this one we actually use a table, right? What's T of 4? 5.7. What's T of 2? 8.3. 5.7 minus 8.3 all over 2. Okay, so this right here is your x value, your input. This is your y value, essentially, your output. So it asks me between 4 and 2. So 4 gives me this value, because we don't have a function to plug it into, right? It's just giving us the values. And then we have 2 gives me 8.3. So I'm doing t of 4 minus t of 2 all over 4 minus 2. That's just a slope formula. Y minus y over x minus x. So for t of a, so for a there, you would get negative 1.3. Is that right? Okay, let me pause that for a second. I don't want to assume this is easy for everyone. I just did the slope formula with a table as given. We don't have points. I mean, we have points essentially, right? Those are all points. Those are all points, so I lined them up into the slope formula. What was the average temperature change for 4 to 2? The average temperature change is negative 1.3 Celsius a minute. Okay? Does that make sense? Another reason it makes sense is because look at the table. As the time's getting higher, your temperature is what? It's dropping. So it makes sense that we have a negative average. Right? Our temperature is going down, therefore it has to be a negative average, okay? So now I want you guys to do these three. Same thing I just did. I want you to do it for all three of them here and see what you get, and I'll put them up in a second.